To now a generalization of what we did into last videos where we showed that C plus can be converted to any two qubit states for AB using LOCC. But this time we will take that any two Qudit states can be converted to any two cubic states. So yeah, we still convert to two qubit state, but at the beginning we take a two Qudit state. So it's not just the states CA plus, but like we just take this, That's our stuff at the beginning. We can write it like this. But like if we want to transform it into a pure state, we need first to remember that what we want to have is this, thanks to the Smith decomposition. A equals 0 to d minus 1 of lambda I of AB with the sum of I equals 0 to d minus 1 of lambda I squared is equal to 1. And so if you apply LSEC, so we do first a local operation by adding a Qudit auxiliary. So basically we have like phi 1 of A prime AB is equal to 0 A prime xert 1 I going to 0 to d minus 1 on 1 of square root of t of I AB. And after we want to apply a local unitary U. So Alice has access to the systems A prime and her Qudit A, and she applies this local unitary to transform into state and integrate the amplitude that she wants, like what coefficients she wants. So basically, she apply her unitary on prime I. So it just gives us that's how we define the unitary. And so if you apply this unitary, ARPC becomes this. So it just equal to sum of G equals 0 of G minus 1 of G prime of A of sum of I equals 0 to G minus 1 of MGI square root of D of GIAB. And when we have this, we can just measure stuff. The auxiliary Qudit A prime to the computational basis G prime, and depending on the result of the measurement, the post-measurement system is projected onto the state itself. So we have C3 of G equal to G of A prime, so 1 square root TPG of sum of I equals 0 to the minus 1 of MGI GEAB. And so after let's communicate these results of measurements G to Bob with a classical canal. software Bob can correct it uh, depending on the result of your receive G. I can apply a correction with a VG on here Qubit B to just retake the untangled states onto the per state that he wants. So you just apply a correction if needed. And that's it. This way the protocol will succeed no matter what happens. And so in the second case, if we want like a mixed states, like mixed states can be written as density matrices like this. Where pk like is equal to 0, and I can even write it like this if you prefer. And the sum of k of pk equal to 1. So if we use LOCC, like Alice and Bob just use a generator of a random number with a classical equivalent mechanism to selection a k index with a probability of pk exactly. They just execute the LOCC protocol that we apply to a per state to fabricate PKO-FB. And so, yeah, we just do this, and thanks to statistics, like the global statistics of the we will made, making a big number of realization without observing explicitly the choice of the random choice. The density matrix will like correspond to what we want. So it just like we apply the depth of per state protocol many times with a d that will represent the probabilities. And so yeah, to conclude, using an ancilla, you need local U and a measure with classical communication and error local correction with a statistical mixture probabilistic. The initial state of qubits maximally intricate can convert any two qubits or AB.